Gravitational field of the Earth, we denote it by this G, and we express it in terms of gravitational Newton's laws of gravitation. That would be G, mass of the Earth, upon radius of the Earth whole square. Yes or no? But what if this is our Earth, and what if I have this, I'm calculating what is the value of field here at this point P. Then the gravitational field G with height G at this point H, I mean at a height H, is given by Gm by R plus H whole square. If this works for any height, for any H, whether H is very, very large, H is very, very small than R, it works for everything. But if H is very, very small than R, I showed you in the class how GH can be written as Gm by R square 1 minus 2H by R. You remember this? You have it in your notes?
Yes, sir.
Yes, sir.
Yeah, all right, okay. So this is the variation of G with height. If you want to see how it varies, I mean, this is one way to write it. The other way would be GH is equal to this Gm by R square is nothing but our original G. So you do this 1 minus 2H by R. Whichever is easier for you to remember, you remember that. Fine. Now, what happens if we go inside Earth? Let's say we dig a well and we descend to the bottom of the well.
R minus H.
Yeah, yes, that is something happens, but something else also works with it. So let's see what happens. Variation of G with depth.
Decreases.
So this is our Earth, and we have descended somewhere here at a depth D. So G at D would be how much? Using Newton's law of gravitation, you say it's G m by R square.
Sir, won't it be the same? We just have to subtract the D length, right?
It won't be the same. That's what we are saying. Okay, fine. That's subtraction of D length. So in the denominator, you want to write what? R minus D?
Yeah.
Yeah, all right. So this is it. However, gravitational force is attractive in nature always. And now at this point, if you're considering, you will only have to consider the mass of this part of the sphere of the Earth. So instead of m, you would have to talk about m dash now. M is the total mass of the Earth. Can you find m dash? So this is the correct formula. So numerator is also reducing. Denominator is reducing and numerator is also reducing. Now, which is reducing more will decide whether the gravity G value is decreasing overall or increasing. Find out this m dash, no? This small sphere.
4 by 3 by R square. So, sir, if you can give us the length of D, then we can find out.
All right. So D is D, that is known. Mass is m. The radius of the Earth is r.
Okay.
So this is given to us. So find the density of the Earth. Assume the density to be constant. So m dash in terms of m, this would be mass per unit volume 4 by 3 pi r cube. This is your density, is it not? Multiplied by the new volume, which is 4 by 3 pi r minus d whole cube. Is it fine?
Yes, sir.
Making sense now? Substitute it here now. Then instead of g m dash, you write all this entire this thing. Okay, so let us cancel out this and this, and what we have is gm r minus d upon r whole cube. That's, we have taken care of the numerator. Do you see that? It's g, but not the original mass of the earth, but only that white part of the earth. So but there was already some denominator, this one, we shouldn't miss that, r minus d whole square. Simplify this quickly and let me know what you are getting. You have to express gd, or value of field at a depth d, in terms of g into something. Can you do that? Are you getting this?
GD is equal to. Yes, sir.
Yeah. So gm by r square, that is what this g is. So you can segregate that and then cancel out the powers and just simplify it. You will get this. Right. So if I have to plot how the value of g varies as I move from the center of the earth to, let's say, Mount Everest, can we do that? All of you, please plot that. By the way, this, note that equation 1 is valid only for small h. So while you're drawing the graph, you must take this one. You must take equation 3 because this is valid for everything, right? So instead of taking equation 1, you have to take equation 3 here. So I'll write 1 point for you. Okay, so that 1 point is when the radius is exactly r, then the value is gm by r square, which is exactly equal to g. So this I've given you. Now tell me what happens before r and what happens after r. What kind of variation do you get? And g at d. So this is what is going to guide you. Yeah, g at d. Now, as you move away from r, g value is decreasing, and is this graph is matching this format. So it's a linear decrease in terms of d. So from here, it's decreasing like that, like that, like that, and going. As you are increasing d, the value of g keeps on dipping like that. And what would happen then after this? After this, it is decreasing. And how is it decreasing? According to equation 3. Now tell me, if we are increasing h, if you're going away, if you're increasing h, then g value is dipping, right? And it's dipping what? Linear decrease, quadratic decrease, cubic decrease. What kind of decrease do you see? Here, g is proportional to r on this side, and here g is proportional to 1 by r square, or g is decreasing as inverse square law, whereas in the first case the g is, if you're going from here to here, then it's increasing. If you're going from the opposite way, then it's decreasing, the same thing. So it's proportional to r basically.